All right, let's take a look at some workbook problems. This is from Chapter 2, the beginning of our workbook. We got problem number 1. We have a position versus time graph on the right. Shows the position of an object moving in a straight line for 12 seconds. All right. What is the position at 2 seconds? All right, you can read that right off the graph. 2 seconds looks like it's at 10 meters. And at 6 seconds, it looks like it's at 20 meters. And at 10 seconds, it looks like it's at 40 meters. All right, just read that right off the graph. That's pretty simple. What is the object's velocity during the first 4 seconds of motion? They're going to ask about velocity, and so this is a position versus time graph. But the slope, of course, is a change in y. Our y variable is x, so we got delta x divided by our horizontal variable, which is t. And that, of course, is average velocity, right? That's the average velocity. That's the definition of it. So, all right, so we're just going to calculate some slopes, I guess. So let me grab a point. We got 0 seconds, 0 meters. And here we got 4 seconds, 20 meters. And here we have 6 seconds and 20 meters. And up here we have, 10 seconds and 40 meters. And then finally we have 12 seconds and 20 meters. I think we're going to probably need all this to calculate our slopes. This shouldn't be too difficult. So velocity from 0 to 4 equal delta x over delta t, 20 meters minus 0 meters over 4 seconds minus 0 seconds. And what is that? That's 5 meters per second. All right, so that's a positive 5 meters per second from here to here. V equals 5 meters per second from there. That's positive. That's positive. That's going to the right there. What is the velocity from 4 to 6 seconds? Well, the whole time it's at 20 meters, right? 20 meters the whole time. This is at rest, right? It's at rest. It's at 20 meters now and 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 now. It is at rest. Now, you also could have looked at the slope. That's also a 0 slope. So therefore, we got 0 velocity, right? So V equals 0 from 4 to 6. What is the object's velocity from 6 to 10? 6 to 10, we got 6 to 10 is, let's say, we got 40 meters minus 20 meters divided by 10 seconds minus 6 seconds. I guess that's 5 meters per second. Again, same speed. It looked like in the graph, now this is a sketch, so it's kind of hard to see, but if you look in your paper, it looks like those slopes were the same. So V is 5 meters per second from here to here. And then on my graph here, it looks steeper here. I'm not sure. Yeah, I do it steeper here too. So this looks like it's going to be moving faster. And these are all to the right. These are positive values. This thing's moving to the right. 10 to 12, from 10 to 12. All right, so again, we have a delta x over delta t, and our delta x in this case is, we got, I'll go 40 meters minus 20 meters divided by 10 seconds minus 12 seconds. All right, so that's 20 divided by, that's 10, negative 10 meters per second. Yeah, right, negative 10 meters per second. So that means it's to the left. It's moving this way. It's moving to the left, 10 meters per second. So that's what that negative tells us. So V equals negative 10 meters per second, or 10 meters per second to the left. All right, so there you go. So the slope is really important in these graphs. You have to be able to read, obviously, the different positions from the graph too. But slope is really important in a position versus time graph because it tells us the velocity of the object. All right, let's erase. sketch a position versus time graph for the following motions. Include a numerical scale on both axes with units that are reasonable for this motion. Some numerical information is given in the problems. For other quantities, make reasonable estimates. Note, a sketch graph is a hand-drawn rather than laid out with a ruler. Oh, guess I won't be using my ruler. Even so, a sketch must be neat, accurate, and include axis labels. All right, so a student walks to the bus stop, waits for the bus, then rides to campus. Assume all the motion is along a straight street. All right, so we got, I'm going to have our student start at position 0. Why not? All right, so starts here. Sounds like a college student to me, because riding to campus on the bus. All right, so we're going like this, and a student walks to the bus stop. Okay, we're going to assume that walks at a constant rate, so not too fast though, maybe, and we're going to go in meters here, and this will go in seconds, and 1/1000, 1/1000. I'll go meter per second. So student's going to go meter per second, and let's say so we'll go 200 meters to the bus stop. 200 meters to the bus stop, and at a meter per second, that's going to take 200 seconds. All right, a couple minutes. A student walks slowly. Oh, a student walks to the bus stop, waits for the bus. All right, gotta wait for the bus. How long does it wait? I don't know. That long. Let's go another 100 seconds. So 300. I already have my units. 300 seconds. And then it gets on the bus, and of course the bus is going to move faster, and so the bus is going to be steeper. Something like this. Bus goes faster than that. Let's see if this worked out. There's 100. Let's go, let's say that's 500. 500 seconds. And let's say if that's 200 meters, 2, 4, 6, 8, 10. I go 1,000 meters, something like that. And all right, let's see if that's a reasonable speed for our bus. We had looks like you went 800 meters in 200 seconds. That's only 4 meters per second. Well, that's no good. That's no good. That's a slow bus. That's a slow bus. That's a really slow bus, right? That's only about 8 miles an hour, which might be an average speed of it. Let's make that faster. Let's make that faster. We're gonna go, I don't know, 1,200 meters, and I'm gonna go another 100 seconds. There you go. That's probably better. So then what did we go? We went 1,000 meters in 100 seconds. That's 10 meters per second, or about 20 miles an hour. All right, it's a slow bus. It's a slow bus. Anyways, so there you go. There's there. Okay, now a student walks slowly to the bus stop. All right, I'm going to keep that. Then realize he forgot his paper. All right. I'm going to keep that. There's my slow walk. My slow walk's right here. Walk to the bus stop. Realized forgot the paper. All right. So, my student's slow on the uptake. slow on the uptake. And what he did is, so he walked slowly to the bus stop, hung there for almost 2 minutes, and oh, wait a second, I need my psychology report, right? So then hurried home, right? Maybe go twice as fast, right? In a hurry, because you got to get back to the bus. Something like that. All right. And there's the quick walk home. Notice other direction, ended up at the same place he started, and much steeper slope because he's scurrying quickly to get his psychology paper. Quarterback drops back 10 yards from the line of scrimmage and throws a pass 20 yards to receiver who catches it and sprints 20 yards to the goal. Draw your graph, the football. Think carefully about the slopes, what they should be. All right. Where he snaps the ball, I'm going to make that 0, right? So snaps the ball and drops back 10 yards. All right. Let's see. So here's a negative 10 yards, negative 10. And this is in yards. This will be in seconds again. I'm going with seconds. So starts here and drops back, snaps football, goes backwards, something like that. And let's see. Let's say that takes him, how long would it take? Let's say 2 seconds. It takes 2 seconds to drop back. And that's 5 yards per second. All right. Yeah. All right, I'll buy that. And then throws the ball. Now, you throw the ball. That's going to be faster than you're running, right? You can always throw that faster than you're running. So then he throws it 20 yards to the receiver. All right. So the receiver is going to be at 10, right? Threw it 20 yards. So something like this. Something like that. Significantly faster. Right? Then that, all right. So a little over twice as fast. And then the person catches it and goes 20 yards to the goal. All right, so 20 yards from there. Here's so 20 is this big. So here we go. So it looks like that's at 30. And you can't run as fast as you can throw a ball, so it's going to go something like this. Something like that. All right. And that might take, let's see. So this was probably about, I don't know. Maybe this is 3 seconds. I don't know. And then, so in that case, we had 20 yards divided by 3 seconds was 20 divided by 3. 6 seconds? 3 meters per second, or 3 yards per second. It's not real fast. That's not real fast. Maybe we'll go 6 seconds. Maybe we'll go 5 seconds. I don't know, something like that. All right. Interpret the following position versus time graphs by writing a very short story of what is happening. Be creative. Have characters and situations. Simply saying that a car moves 100 meters to the right doesn't qualify as a story. Your stories should make specific references to information you obtain from the graphs, such as distances moved or times elapsed. All right. Or speeds traveled. First thing I would do in a problem like this is let's figure out what our speeds are. And you could calculate, so slope equals delta x over delta t. And we have, for delta x, we have 10 miles minus 0 divided by 10 seconds minus 0 is 1 mile per second, which of course is 60 miles per hour because there's 60 seconds on it. 60 miles per hour because there are 60 I'm sorry, these aren't seconds, these are minutes. A mile a second would be quite fast. It's minutes. Minutes. That's not seconds, that's minutes. Minutes. All right. So that's minutes, not seconds. And I was looking at miles per second. That's pretty fast. So 1 mile per minute or 60 miles per hour. All right. So right here is 60 miles per hour. Make sure you're calculating this, right? And then we're at rest. And then calculate that. That's going to be going slower. I'm going to leave that to you. And then this is at rest. It got zero slope. And then it looks like we're at 60 miles an hour again. And then we're at rest again. And then this one was actually steeper, right? This one was actually steeper. And you should calculate this. I calculated it at 75 miles per hour. And, all right. So, this is looking like this person's on the thruway, or maybe they're in Los Angeles, they're on a freeway, or something like that, and going 60 miles per hour. So, I would say Gilbert was driving along the freeway when he had this terrible thought that he forgot something. So he did an emergency park job next to on the thruway, on the shoulder of the thruway. Never do that. It's dangerous. But he was overwhelmed with a sense of dread. And he sat there and thought about it for 10 minutes and couldn't think about what it could possibly be. So then he got back on the thruway, but he was really concerned that he was forgetting something. So he went at half speed, and it was like about 30 miles per hour for 10 seconds. 10 minutes. And then said, I got to pull over again. Pulled over again. There's people honking behind him and everything. Like, I got to figure out what this is. So he pulls over, thinks about, what am I forgetting? I'm forgetting something. And then, I think I'm fine. So he gets back on through and he's cruising around 60 miles an hour. And then all of a sudden, just completely awash in dread, pulls over again, thinks about it. And after 10 minutes of thinking, goes, I forgot to feed the baby. Right? So then he drives home very fast, 75 miles an hour, breaking the law, but got to get home to feed the baby. So drove home and fed the baby. And the baby was fine. All right, so there you go. There's our story. The story of Gilbert and forgetting to feed the baby. Oh, a sprinter. Well, they kind of told the story there. If you take a look there, we got a curve like this, and it turns out that most human beings in a sprint, you got sprinters, they can't. They speed up for fairly quickly in a race. This is a 100-meter race, and they accelerate the beginning. And then they hit a top speed fairly early. And a good sprinter can maintain it, or at least come close to maintaining the top speed to about the 70-meter point. And then they usually start slowing down. I think all sprinters slow down. Certainly by the end of the race, they're slowing down. You can't hit top speed and maintain that for 100 meters. It's just not possible. Human beings can't do that. If you see a sprinter pulling away, what's happening is the other people are slowing down more than the sprinter that's pulling away. So anyways, you had something like this. And it got pretty linear here. We had this curve where the person started. So they started the race. And after about 6 seconds, this thing got pretty linear at about the 6-second point. And it stayed linear, according to this, to the end of the race, which is 100 meters. Right? Races generally, that's a big race in track, the 100-meter dash. It's the shortest sprint in outdoor track. So we had 100 meters, and this is pretty linear. I calculated that slope to be about 20 meters per second. So the sprinter started from rest and hit top speed at around 6 seconds and maintained that speed through 9 seconds. The top speed of 20 meters per second. So that's a very good sprinter. That's a world-class sprinter there, finishing 100 meters in like 9 seconds. Yeah, that's pretty good. 2 football players. We got Brutus and Fred. Oh, it looks like, all right. So it looks like this is kind of a kickoff, I guess. Brutus is at the 60-yard line, or 60 yards away from the goal line. I don't know. It looks like Fred starts out at the 10-yard line. It looks like they're setting up their field like this. where this might be a goal line in football, and they're calling that 0. There's a kickoff. And, all right, so it looks like Fred gets the ball at the at 10 meter. This is in yards. Here's a football field. So this is 0, and this is in yards. There you got 10 yards, and okay, it looks like Fred gets the ball here, and it looks like he runs at a constant speed to the end zone, which is at 100 yards, right? So they kick the ball here. They actually kick it from the 35-yard line. So they would kick it here. I don't know why it's at 60 here. But anyways, maybe the guy written it didn't understand football. But so it looks like they kick the ball off, and the problem starts when Fred gets the ball. And he's going to start running this way. And he's just going to run at a constant speed till he gets to the end zone at the 100-meter point. And Brutus starts at 60, so he's like here. He's like here. And they kick the ball, and here's Brutus, here's Fred. So what's going to happen is, Fred's moving faster than Brutus, and he goes, whoa, and he sidesteps him. And then Brutus turns around and runs towards him, but Fred's too fast for Brutus. Brutus is running slower. If you take a look at that slope, you can see that Brutus is slower. So there's a kickoff. Fred gets the kickoff at the 10-yard line and runs at a constant speed of, what's Fred's speed? V of Fred. Let's see. He travels 90 yards. 90 yards in how many seconds? 12 seconds. All right. So he's running at 7.5 yards per second. All right. So that's Fred's speed, and it's a constant speed this way. Brutus, calculating his speed, he goes 20 yards in 5 seconds. And that is negative 4 meters per second. All right. Yeah, so Brutus is running to the left at 4 meters per second. And then Fred runs past him. And he runs past him at the 30-yard mark, right? They're at the same position wherever 30 is. So 30 might be here. So at this point, they kick off, and they're at the same position at 30. And then Fred passes him and pulls away because he's a faster runner, right? The faster runner there. So V initial Brutus is negative 4 meters per second. And then you can calculate his, and then I think he's 5.5. That's not meters per second, that's yards per second. Yards. I'm not used to using these English units. So 4 yards per second, not meters, that's yards. 4 yards per second. And then he chases him going 5.5 yards per second, but he's not going to catch him because Fred's too fast. Fred's going 7.5 yards per second. All right, there you go. There's our stories. Fascinating stories. It's story time in physics class. We got a position versus time graph, A and B. At 1 second, all right, 1 second's about right here. At 1 second, is the speed of A greater than, less than, or equal to B? All right, well, let's see. This is a position graph. And so it's not a speed graph, but we can find the speed from it by finding, let's see what the slope gives us. Slope equals delta x over delta t. Oh, beauty, that's speed. That's speed. Beautiful thing. Always do this because you get in the habit of doing this. Right now, it's like it's always speed, but it's not always going to be speed. It's going to be all kinds of stuff. So get in the habit of writing out the slope and then go, okay, I know what delta x over delta, that's speed, right? It's going to be other things later in the year, but for now, it's speed. Always write out the slope. So what do we got? All right. So the slope is the speed. All right. Well, they never have the same slope, so they never have the same speed. In fact, B, it looks like the way I drew it. Oh, well, it's at an angle, actually. I kind of drew it more horizontal than I should have. So B is definitely slower than A. A's got a steeper slope. A is faster. So, the velocity of A is always greater than the velocity of B, or the speed. Either way. Because A definitely has a greater slope. Do the objects ever have the same speed? No, they do not. They do not. Nope, they do not. They do have the same position, though. Right at that point. It looks like it's about 3 seconds. At 3 seconds, same position. Same position, different speeds. Same position. Right there. B is at meters, and A is at reference meters. Draw a position versus time graph and velocity versus time graph for an object that is at rest at 1 meter. All right. So we got an object that's just sitting at 1 meter. It's at rest at 1 meter. What's the position versus time graph look like? Well, it's always at 1 meter. So I bet it looks something like this. Here's X. Here's 1 meter. That's what it looks like. It's always there. It's always there. Boom, 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 boom. Where is it now? It's at 1 meter. Where is it now? It's at 1 meter. Where is it now? It's at 1 meter. It's at rest at 1 meter. All right. What's the velocity look like? Velocity in time looks like this. What's the velocity? It's at rest. What's it now? It's at rest. Now what is it? It's at rest. Now it's at rest. Because it's always at 1 meter. It's just sitting there at 1 meter. Just sitting there at 1 meter. It's not moving from 1 meter. It's at rest. All right. So there's our 2 graphs look like. Figure shows 6 frames from a motion diagram, 2 cars, A and B. Draw a position versus time graph and a velocity versus time graph for both cars. All right. And something like that. That might not be perfect, but these should be equally spaced. I didn't do a great job, but you have your drawing. Go with that. Here's 0, and here's time 5. All right. And one thing you should notice is at 3, they line up. All right. So I'm gonna graph this stuff, and what I'm gonna do is I'm gonna set up my coordinate system like this. Here, maybe I'll use red. I'll use red just to set it up. So there are my dots. So I'm gonna set up a coordinate system like this. There's X. Hopefully you can see that. I don't know if you can see that or not, but there it is. And all right, so there's our origin. So this one's A is going to start at a positive position, and B is going to start at 0. All right, so what do we got? Position versus time. Position versus time. B starts at 0, and B is going faster than A. You can see they're spread apart, so go something like that. This is B. And then A actually starts at a positive position to start with at time 0. So I'm going to put it here. There's a positive position there. And it's going slower. And they are at the same position at time 3. So I'm going to go kind of like this. So I'll go, there's 3. And this is A. This is A. So it's going slower. A's going slower. You can see they're closer together. It's going at a constant speed. They're both going at a constant speed. And they're at the same position at 3. So do the cars ever have the same position? Yeah, they do. At 3. At 3. This is a dot there. So at 3, they have the same position. Oh, I forgot velocity versus time. So velocity versus time graph looks like this. All right, A is slower. B almost looks like it's almost twice as fast. Something like that. All right, so B is like that and A is like that. So yeah, so do the cars ever have the same position at one instant of time? Yes, they do. If so, which frame number? 3. It's same position at 3. Draw a vertical line through your graphs to indicate this instant in time. All right. All right, so there it is there. You can't tell on the velocity because nothing special happens there at 3. But we can tell from this graph. It's where the two lines intersect. All right, let's try 7. Below are 4 position versus time graphs. For each, draw the corresponding velocity versus time graph. Directly below it, a vertical line drawn through both graphs should connect velocity x at time t with position x at the same time. There are no numbers, but your graphs should indicate relative speeds. All right. So A, we had, it's a constant negative velocity. There you go. There you go. Nothing special happens here. This is when it's at position 0. Has no effect on velocity at all. All right. So that was A. It starts at some small positive position. And then it goes forward at a constant velocity. And then is at rest at a more positive position. So this is slope of this graph is velocity. This has a 0 slope. So this is starting out at a 0 velocity. 0 velocity from there to there. Positive slope. Here we got a positive velocity like that. Positive constant velocity like that. And then we're 0 again. We're at rest. 0 velocity, 0 slope. And this is, oh man, that wasn't B, that was C. That's terrible. That wasn't B, that was C. I went down. That was C. That was C. It wasn't B, it was C. All right. So let's take a look at B though. Now let's take a look at B. Now let's look at B. Now that we already mislabeled C, let's take a look at B. All right. So there we go. We got B. Looks like this. Starts at a negative position and does something like that. And that should be a straight line, even though it might not look like that. That is a positive velocity. So here's my axis, and this is a constant positive velocity. All right, nothing particularly interesting happens there other than the object is at position 0 at that point. All right, and then finally we have D. All right, so we're at a negative position, and then we go to a constant positive velocity or velocity to the right, and then we're at a positive position, something like that. All right, we have a change here, so I want to make sure my graphs line up. And all right, so we had 0 velocity here is at rest. And we had a constant positive velocity here, and then we had a 0 velocity again. Should look something like that. All right. We had something that looks like this. It gave us velocity. Boom, 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 boom. Time, velocity. And however big this is, that looks like it's about the same size, only negative. And position. All right, so it looks like this thing's at a constant velocity. Let's see, we're going to start everything at 0 as it says. So this goes at a constant velocity, 0 velocity, constant negative velocity. So this is a constant velocity, so this would be a constant slope because the slope of a position versus time graph is a velocity. And then it has a 0 velocity, so it's going to remain at that position, wherever it is, right there. So that should be straight across. And then it looks like it has an equal negative velocity for an equal amount of time as it did before. So this thing is going to actually have, we got negative velocity. It's going to end up where it started. So it should look something like that. I'm going to let you write a description of that motion. I just described it, so anyways. Figure shows a position for a time graph for a moving object. At which letter or points is the object moving the slowest without being at rest? All right, so it's got to be moving, right? So it can't be A, C, or E. It's not moving. Those are at rest. So we're looking for the smallest slope, and that would be B. A is B. All right. So I'm moving at the slowest, and that's actually it's going at a positive velocity. Where is the object moving the fastest? Well, that's D. D, steepest slope, right? Okay. So that's why it's going fastest. It's in a negative direction, but that doesn't mean it's slower. It just that's negative. That's left. That's left. Negative isn't less. Negative's not less in this case. Negative just indicates direction. All right. C. When's the object at rest? Looking for zero slope. It looks like A, C, and E. Boom, boom, boom. It's at rest. D. When is the object have a constant non-zero velocity? B and D. Right. So we're looking for a non-zero slope, and it has to be constant slope. So B and D has both of those characteristics. Is the object moving to the left? All right. So for the left, we're looking for a negative slope. So that is D. It's moving to the left at D. All right. I guess the parachute, they're just saying like it instantaneously slows her down. Of course, it would take a little bit of time to do that, but this is uniform motion. So we're just going to assume that you pop the parachute, and it just gives this huge jerk, and then you just go to constant speed on the rest of the way down. So we got this Y. She opens it at 1,500 meters, and she goes down at. She then slowly goes down at 5 meters per second. All right. So her speed is 5 meters per second. How long does it take? All right. So speed is delta Y over delta T. So delta T, therefore, the time it's going to take her to fall is her delta Y over V. And we know her delta Y is going to be negative 1,500 meters. That's how far she's going to drop. Negative 1,500 meters because it's downward. And her speed is going to be minus 5 meters per second. So I guess that's, what do we got? 15 divided by 5 is 300 seconds. All right. So she's going to make it to the ground in 300 seconds. And if we're assuming constant speed after she pops that off, looks something like that. All right. That is A. That is A. That is 10A. A rabbit hops at a steady speed of, all right, so we got a rabbit. All right, so notice I used Y there because it was a vertical problem. She was coming down, I used Y instead of X. Generally, we'll use X for horizontal. And this is this problem, we have a rabbit. And hopping horizontally, I would imagine, at a steady 1 meter per second for 4 seconds. All right. All right, so for 4 seconds, she's going 1 meter per second. So I'll just go, all right. So she goes 4 meters in 4 seconds. There's 1 meter per second. Hopping along, and then sees a coyote and instantly increases to 3 meters per second. All right, so gonna go faster. And I think this would get down to 16 meters, and this would be 8 seconds. That would give me a speed of 3 meters per second, I believe. Why don't you check that out? Should have done something like that. You can find that speed there. All right. Quarterback Bill throws the ball to the right at a speed of 15 meters per second. All right. 15 meters per second. It is intercepted 45 meters away by Carlos, who is running to the left at 7.5 meters per second. Carlos carries the ball 60 meters to score. Let X equal 0 where the Bill throws the ball. All right, so Bill's here, and he throws the ball at a speed of 15 meters per second, and it goes 45 meters. All right, so goes 45. I'll say 45 meters is here. And he throws it 45 meters. at a speed of 15 meters per second. So his speed that he throws the ball is 15 meters per second. And it goes a distance of 45 meters. Right? So how long does that take? Alright, well, v equals delta x over delta t. And therefore, delta t equals delta x over delta over v. Just doing a little algebra. So we got 45 meters divided by 15 meters per second. That's 3 seconds. That's 3 seconds. 3 seconds to get to 45 meters. And then it's intercepted by Carlos, who carries the ball 60. So Carlos is going this way. He catches the ball and goes back to the left. So we're going to need a negative velocity. And he actually makes it to, he runs 65 meters, right? No, 60 meters to score. So I guess that's negative 15 meters. So Carlos, I'm going to have to erase this. I'm running out of room. I have to erase that. All right, so Carlos goes negative 15 meters like that because he had 15 to 45 and you get 60. All right. I don't know who's using meters on a football field, but anyways, they are. And so then, and I think that would take something like that. So it's going to take a little while longer because it can't run as fast. I think that takes 11 seconds. 11 seconds because he is running at 7.5 meters per second. I want to double check that, make sure that's right. He had a speed, he's running at a negative 7.5 meters per second. Double check that, make sure I got that right. At 11 seconds, he's at negative 15 meters. All right. And then finally, all right, this next one's kind of a strange question for this. The height of a building is proportional to the number of stories it has. If a 25-story building is 260 feet tall, what is the height of an 80-story building? I think I'm going to multiply by ones. I think I am. All right. Because I know that 25 stories equals 260 feet. Right? I mean, we can use a story as a unit of measurement. So 25 stories equals 260 feet. What is the height of an 80-story building? All right, so I have 80 stories, and I want to convert that to feet. So I'm going to multiply by ones. 25 stories. 260 feet. 25 stories. All right. And I think I got 832 feet is the height. By multiplying by ones. All right, so there we go. We had 1 through 11 in your workbook. And, all right. Hopefully that's making sense. Graphing is tricky. It's going to take some work. You got to get used to it. You got to look at slopes. You got to look at positions. You got some things to calculate. But it's not too bad once you get enough practice. So, all right. I will catch you later. Bye-bye.